Allylic systems have a carbon-carbon double bond and one additional carbon attached to that carbon-carbon double bond. So it's a 3-carbon system with something special about that end carbon. That end carbon may have a positive charge. It's missing 2 electrons. That carbon only has 6 electrons in its valence shell, in which case it's a cation. It may be neutral, have 1 electron, and that's a radical. Or it may be an anion, having 2 electrons at that carbon and simply missing a proton. These are all allylic species, cation, radical, or anion, and they have special properties, including being especially stable. Now you know that in our Lewis theory, we write resonance structures to indicate extra stability. In the case of the cation, we picture these pi electrons being shared between these 2 carbons, moving over 1 to being shared between these 2, which leaves the positive charge on the end carbon. In the radical case, we picture 1 electron moving in this direction to share with this electron. And this other electron of the pi system is left on this end carbon. And in the anion, we picture the electrons going the other way. This pair of electrons now becomes shared, and this pair of pi electrons is now on the end carbon. In all of these cases, the resonance structure is intended to indicate this is a more stable structure than normal. But how much more stable and why it's really more stable are completely unaddressed in this Lewis bonding resonance theory. Molecular orbital theory gives us insight into both why allylic systems are more stable and quantitatively about how much more stable. Take a look. For starters, we need to know that each of these species has a p orbital on each of the 3 carbons that all can line up and overlap with each other. So the pi bond has 2 p orbitals, 1 on each carbon, and that end carbon has a p orbital also. These guys can all overlap with each other. And our MO theory of bonding tells us when we have overlapping adjacent p orbitals, those atomic p orbitals result in molecular orbitals, and we have the same number of molecular orbitals as we have adjacent p orbitals. So in each of these 3 allylic systems, the cation, radical, and anion, we'll have 3 MOs because we have 3 atomic p orbitals on adjacent carbons. So on this diagram, I've lined up the adjacent p orbitals with their energy levels at some arbitrary energy. And we see that we have 3 resulting MOs, pi 1, pi 2, and pi 3. One of these is lower energy, and the other is higher energy. The other one, pi 2, is a non-bonding orbital that has the same energy as the p orbitals. The more stable MO, pi 1, is a bonding orbital. Pi 2 is a non-bonding orbital, and pi 3 is an anti-bonding orbital. When we think about how these molecular orbitals actually look like in an atom, we need to think about how the p orbitals interact. The lowest energy MO, the most stable one, has all 3 p orbitals interacting in phase. In the non-bonding orbital, we only have 2 of the p orbitals interacting, and they have 1 node. The center p orbital does not contribute, and this is going to be very important. This center p orbital is the one associated with the center carbon. We'll get back to that and see just how important that is. And the antibonding orbital has 2 nodes, so all 3 p orbitals contribute, but none of them are in phase with each other. So as we actually look at the physical picture this gives us of the molecular orbitals within the allylic system, it looks something like this. Pi 1 is an MO that extends throughout the 3-carbon system. There's this region of space above the plane and below the plane that has a probability of finding electrons, and they each have their own phase. Pi 2, the non-bonding orbital, turns out to be the most important for our analysis of the allylic system. I'll get back to this, but notice that it has 1 node, and the probability of finding an electron in this orbital at the center carbon is non-existent. If there's an electron in this orbital, it will be found at 1 carbon or the other, but never in the center. And the antibonding orbital has 2 nodes. None of the p orbitals are in phase. There are 6 distinct regions in the molecule where the probability of finding an electron in this orbital exists, But because it's higher energy, we won't see an electron in this orbital normally. Now, what does this physical picture of the regions in space that these orbitals occupy tell us about the actual allylic systems themselves? Well, take a look. I've redrawn these MOs to be adjacent to the energy levels, pi 1, pi 2, and pi 3. And we know that as we put electrons in these molecular orbitals, 2 can go in each orbital, and we'll fill that lowest energy one first. So when we have the allylic cation, which only has 2 electrons in it, both of those electrons will be in the lowest molecular orbital, pi 1. They'll be found distributed throughout this allylic system. The allylic cation doesn't have any more electrons, but rather it has a positive charge. And look where the positive charge is. It's where the electron is missing from an orbital. If there were another electron, it would be in pi 2. So the positive charge is in pi 2, meaning the positive charge is at the ends of this allylic system and never at the center carbon. Does this sound familiar? It's the same picture we get from our Lewis bonding theory resonance structures. If we have one more electron, we have the allylic radical. It will be in the non-bonding orbital, and that radical will have a probability of being found at the end carbon or the other end carbon, but never at the center. Again, this looks just like our Lewis bond theory resonance structure picture. And finally, for the anion, there's an additional electron. It also goes in the non-bonding orbital, and it brings with it an extra negative charge, and we know that that negative charge will be in this orbital, pi 2, at the end carbons, never at the center. Again, the very picture we get from our resonance structure theory. And one last question for you. Which allylic system gains most stability from these MOs? The cation, the radical, or the anion? Well, take a look. The cation has electrons only in the more stable bonding pi 1 MO. So it gains the greatest stability as an allylic cation. The allylic radical gains extra stability as well, but it does have an electron in pi 2. And the anion has 2 electrons in pi 2. So of these 3 allylic systems, the allylic anion will enjoy the least special stabilization. MO theory of pi systems is a very powerful tool.